Hi everyone, welcome. If you're watching this right now, you're probably settling in for the night. Maybe you've turned the lights down low. Maybe you're lying somewhere comfortable with a blanket pulled up and the room is quiet around you. That's exactly the right way to watch this. Tonight, we're going to talk about stars, not in a loud or rushed way. We're just going to sit with the subject for a while and let the ideas drift in slowly, the way stars themselves drift slowly through the sky. Stars are very old things, and tonight we're going to think about why, after a very long time, they eventually come to an end. There's no hurry. We have plenty of time. So let's begin. Take a breath. Let your shoulders settle. Outside right now, if the sky is clear, there are thousands of stars visible to the naked eye. Each one is a sun, or something like a sun. Most of them are so far away that the light you're seeing left them before human civilization existed. Some of that light is ancient beyond imagination. And yet every one of those stars, every single one, will someday stop shining. That's what we're going to gently explore tonight. Why stars are born, why they shine for so long, and why eventually they must die. Let yourself get comfortable. There's nothing to do right now, except listen. Before we talk about how stars die, it helps to understand what a star actually is. A star is a sphere of gas, mostly hydrogen, some helium, and tiny traces of other elements. That gas is held together by gravity. Gravity is always pulling inward toward the center. And at the center of a star, the pressure and the temperature become so enormous that something remarkable happens. Hydrogen atoms are forced together. They fuse. They combine into helium. And when they do, a small amount of mass is converted directly into energy. That process is called nuclear fusion. And that energy, that steady, ancient, slow release of energy, is what makes a star shine. It's almost peaceful when you think about it. A star is essentially a very long, very slow burn. Deep inside, hydrogen is quietly fusing into helium over billions of years. And the energy from that process gradually makes its way outward until it escapes into space as light and heat. The sun, that warms the Earth every day, has been doing this for about 4.5 billion years. And it will continue doing it for about another 5 billion years. That's almost 10 billion years of steady, quiet burning. There's a balance at the heart of every star. On one side, gravity is always trying to pull the gas inward, trying to collapse the star. On the other side, the energy from nuclear fusion pushes outward, trying to expand the star. For most of a star's life, these two forces are almost perfectly balanced. The star neither collapses nor explodes. It just sits there stable and quiet, burning through its fuel, very slowly. That balance has a name. It's called hydrostatic equilibrium. It's a gentle word for a peaceful state. The star is in balance, neither too compressed nor too expanded, just right for an enormously long time. Let that settle for a moment. A star is a balance, a long, stable balance between two enormous forces. Gravity pulling in, energy pushing out, and between them steady shining. Stars don't start as stars. They start as clouds. Vast, cold, dark clouds of gas and dust drifting slowly through the galaxy. These clouds are made mostly of hydrogen, the simplest element, and for long stretches of time, sometimes millions of years, they just drift, quiet and cold and dark. But sometimes something disturbs a cloud. Maybe the shockwave from a nearby dying star passes through. Maybe two clouds drift into each other. Maybe the slow gravitational currents of the galaxy simply pull a region of the cloud a little denser than the rest. Whatever the cause, when a region of the cloud becomes dense enough, gravity begins to take over. Gravity is patient. It doesn't rush. But once it begins pulling a region of gas inward, the process continues. The gas falls toward the center of the region. As it falls, it speeds up. As it speeds up, the atoms collide with each other more and more often, and collisions mean heat. the cloud begins to warm. It's a very slow warming. Over hundreds of thousands of years, the center of the cloud grows hotter and denser. It starts to glow, not yet from nuclear fusion, but just from the heat of the gas falling inward. This early not-quite-a-star is called a protostar. A protostar is a beginning. It's a star in the making, still falling inward, still gathering mass, still warming up. For a long time, the protostar is hidden. The gas and dust around it are so thick that light can't get out. If you could look at the cloud from a distance, you might see a warm glow in the infrared, a kind of invisible warmth, but nothing in visible light. The star is forming in the dark, but eventually the pressure at the center becomes so great and the temperature so high that nuclear fusion begins. Hydrogen atoms start fusing into helium. Energy starts being released, and that energy begins to push outward against the inward pull of gravity. The star has ignited. When the fusion begins, the pressure from the energy starts to push the surrounding gas outward. Slowly, over thousands of years, the remaining gas and dust are cleared away. And then one day, in astronomical terms, the star shines freely into open space. A new star. This process from cloud to star can take a few million years, which sounds like a long time, but compared to the star's lifetime, it's almost nothing. Most of a star's life is spent in a phase called the main sequence. This is the long, stable middle of a star's existence. The phase where the star is quietly burning hydrogen into helium in its core, and the forces of gravity and energy are balanced. Our own sun is a main sequence star. It has been a main sequence star for about 4.5 billion years, and it will remain one for about 5 billion more. The main sequence is not dramatic. Nothing much changes, at least not quickly. The star just shines, day after day, year after year, millennium after millennium. How long a star spends on the main sequence depends on its mass. This might seem counterintuitive at first. You might think that a more massive star, one with more hydrogen fuel, would last longer. And it's true that a more massive star has more fuel. But a more massive star also burns that fuel much, much faster. A star that is 10 times more massive than the sun burns through its fuel at a rate roughly 10,000 times higher. So instead of lasting 10 billion years, it might only last 10 million, a tiny fraction of the time. Very massive stars, the ones that are 10, 20, 50 times the mass of the sun, burn brilliantly. They shine with a fierce blue-white light. You can see them from great distances, but they're profligate with their fuel. They burn through it in cosmic eye blinks. Millions of years instead of billions. Smaller stars, on the other hand, burn very slowly and very efficiently. Stars smaller than the sun, called red dwarfs, are so frugal with their fuel that they can remain on the main sequence for trillions of years, far longer than the current age of the universe. The universe is only about 13.8 billion years old, but a small red dwarf might shine for 100 billion years, or even 1 trillion years. So massive stars live fast and die young in astronomical terms. Small stars live slowly and last almost forever. There's something quietly poetic about that. The stars that burn brightest are the ones that die soonest, and the modest little stars burning dim and red outlive them all by unimaginable margins. Let that thought drift through your mind for a while. Let's slow down and think about our own star, the sun. Right now, at this very moment, the center of the sun is at a temperature of about 15 million degrees Celsius. Under pressure, hundreds of billions of times greater than the air pressure at Earth's surface. In that environment, hydrogen nuclei, protons, are being fused together at a steady rate. The process is called the proton-proton chain. It takes 4 hydrogen nuclei to make 1 helium nucleus, and in that conversion, a tiny bit of mass, about 0.7% of the total, is turned into pure energy. Every second, the sun converts about 600 million tons of hydrogen into helium, and about 4 million tons of that mass is turned directly into energy. For million tons per second, that's an almost incomprehensible number. And yet, the sun has been doing this for 4.5 billion years, and it will keep doing it for 5 billion more. The sun is so massive, so enormous, that even burning for million tons per second barely makes a dent over human timescales. The energy produced in the sun's core doesn't just rush outward instantly. It takes a very, very long time to travel from the core to the surface. The interior of the sun is so dense that a photon, a particle of light, can take anywhere from 10,000 to 100,000 years, possibly even longer, to travel from the core to the surface. It bounces around absorbed and re-emitted by gas particles, slowly working its way outward over timescales that dwarf all of human civilization. The sunlight that warms your face today might have been generated in the sun's core before the first humans walked on Earth. Take a breath. Think about that for just a moment. The warmth of the sun on your skin is ancient. The energy in that light was forged deep underground, in the solar underground, before history began. There's something very calming about that thought, something old and patient and steady. The sun has been burning for a long time, but it isn't exactly the same as it was when it first formed. Very slowly, over billions of years, the sun has been changing. When the sun first ignited, it was actually a little cooler and a little dimmer than it is today. Early in Earth's history, the sun was only about 70% as bright as it is now. Over time, as the sun has fused hydrogen into helium in its core, the core has become denser and slightly hotter. And as the core gets hotter, the fusion reactions become a little faster, and the sun becomes a little brighter. This is a very slow change, much too slow for humans or even human civilizations to notice. But over hundreds of millions of years, it is significant. For a billion years from now, the sun will be noticeably brighter and hotter than it is today. So hot, in fact, that liquid water will no longer be stable on Earth's surface. The oceans will begin to evaporate. The atmosphere will change. Life, as we know it, will be in deep trouble long before the sun actually runs out of fuel. But that's a very long time from now. Longer than modern humans have existed by a factor of about 20,000. For now, the sun is stable, middle-aged in stellar terms, still burning hydrogen in its core, still balanced, still in that quiet, steady state called the main sequence. We don't need to worry about any of that tonight. Right now, the sun is well behaved. It is doing what it has always done, slowly, steadily burning, and it will keep doing so long after every single human civilization has come and gone. Now, let's come to the turning point. The turning point in a star's life is when it runs out of hydrogen fuel in its core. Remember, the core is where fusion is happening. That's where the temperature and pressure are high enough for hydrogen nuclei to fuse together. The outer layers of the star are much cooler and much lower in pressure. Fusion doesn't happen there, so a star is slowly, steadily converting the hydrogen in its core to helium. And when the core runs out of hydrogen, when it's been converted entirely to helium, the fusion stops. And that's when things begin to change. When fusion stops in the core, the energy production stops. The outward pressure drops. Gravity, which has always been pulling inward, now has less resistance. The core begins to contract, and as the core contracts, it heats up. The gravitational energy of the contracting gas is converted into heat. Meanwhile, just outside the core, in a thin shell of gas surrounding the helium core, there is still hydrogen. And this shell of hydrogen, now heated by the contracting core, below it, begins to fuse. Shell fusion, a ring of burning hydrogen surrounding a dense, hot helium core. This changes the star. The energy from the shell fusion pushes the outer layers of the star outward. Slowly at first, then more and more, the star begins to expand. And as it expands, those outer layers cool. As they cool, they change color, from yellow to orange, from orange to red. The star is becoming a red giant. The red giant phase is one of the most dramatic transformations in a star's life. But in cosmic terms, it happens slowly, over millions of years. For a star like the Sun, the red giant phase will happen about 5 billion years from now. When it does, the Sun will expand enormously. Not just a little, enormously. It will swell outward until it is perhaps 100 times its current size. Maybe more. At that size, the Sun would swallow Mercury. It would swallow Venus. And it might even reach out to where Earth is now. Whether the Earth survives the Sun's red giant phase is actually not entirely clear. The answer depends on how much mass the Sun loses during that phase, and stars do lose mass as they expand. If the Sun loses enough mass, its gravitational pull weakens, and Earth's orbit would drift outward, perhaps fast enough to stay ahead of the expanding surface. But even if the planet survives, the surface of the Earth will be utterly unrecognizable. The temperatures will be far beyond anything capable of supporting life. The oceans will long since have boiled away. The Sun's red giant phase will last for about 1 billion years. A long time, but brief compared to its main sequence life. During this time, the star is not stable. It's puffed up, its outer layers cool and loosely held. It's more complicated inside with a dense hot core and a vast tenuous envelope of gas. Let's pause here for a moment. The red giant phase is a kind of old age for a star. It has moved past the long, steady middle of its life and entered something more turbulent. Not violently turbulent, just less settled. There's something recognizable about that. Things change as time passes, even for stars. As the helium core contracts and heats up, during the red giant phase, something important eventually happens. The temperature in the core rises high enough for helium itself to fuse. Helium fusion requires much higher temperatures than hydrogen fusion. Hydrogen fuses at around 15 million degrees. Helium fusion requires temperatures above about 100 million degrees. But the contracting helium core eventually gets that hot, and when it does, a new process begins. 3 helium nuclei fuse together to form a carbon nucleus. This process is called the triple alpha process because helium nuclei are also known as alpha particles. The triple alpha process is one of the most important nuclear reactions in the universe. It is the process that creates carbon, and carbon is the backbone of all life on Earth. The carbon in your body was made in the core of a dying star. The calcium in your bones, the oxygen in your lungs. These elements were forged in stellar cores and scattered across the galaxy. When those stars eventually died, you are, in a very literal and scientific sense, made of ancient stars. Let that thought rest for a moment. The atoms in your body have a history that stretches back billions of years and thousands of light years. They were made in nuclear reactions far more powerful than anything humans have ever created. And they traveled across space, condensed into a new star system, formed a planet, and eventually became part of the chemistry of life. It's a remarkable thought, and a calm one. You are part of a very old story. Now, helium fusion begins in the core of the red giant star. For a while, the star stabilizes again. It has a new source of energy. The core is burning helium. The outer layers settle somewhat. The star is in a new phase of its life, sometimes called the horizontal branch or the red giant branch, depending on the type of star. But this phase is shorter than the main sequence, because helium is a less efficient fuel than hydrogen. And because the star is burning more brightly now, the helium runs out faster. When the helium in the core is exhausted, the same pattern repeats, one level up. The helium core contracts, gets hotter, and a shell of helium around the core begins to fuse. And around that, a shell of hydrogen fuses as well. The star now has a layered structure, a dense core of carbon and oxygen at the center, a shell of helium burning above it, a shell of hydrogen burning above that, and a vast tenuous envelope of gas making up the outer layers. This phase is called the asymptotic giant branch. It's a mouthful, but the idea is simple. The star is a red giant again, but puffier and more complex inside. Stars in the asymptotic giant branch phase behave in interesting ways. They can pulsate, expand, and contract, not dramatically, but rhythmically over periods of months to years. They throw off gas from their outer layers in slow, steady stellar winds. Gas that drifts away into the surrounding space, carrying carbon and oxygen and other elements forged in the stellar core. These stellar winds are gentle, in a way, not explosive, just a slow shedding of material. Over thousands of years, the star loses a significant fraction of its mass this way. The outer layers, already loosely held by gravity in this puffed-up giant phase, drift away on those stellar winds. Slowly, the outer layers are stripped away, and the dense, hot core, the carbon-oxygen heart of the star, begins to be exposed to the surrounding space. The star is approaching the end of its life. As the outer layers drift away from a dying star like the sun, something beautiful happens. The gas that has been shed forms a shell or several shells expanding outward around the star. And as the hot core of the star becomes exposed, it begins to emit intense ultraviolet radiation. That radiation illuminates the surrounding gas. It excites the atoms in the gas, causing them to glow. The result is a planetary nebula, a shell, or sometimes a series of shells, or complex flowing shapes of glowing, multicolored gas surrounding the dying star. The name, planetary nebula, is actually a misnomer. It has nothing to do with planets. Early astronomers named them this because in small telescopes they looked a little like the disks of planets, round and greenish. But they have nothing to do with planets. They are the cast-off outer layers of dying stars, illuminated by the light of the exposed stellar core. Planetary nebulae are among the most beautiful objects in the sky. The Helix Nebula looks like a vast eye peering through space. The Ring Nebula is a glowing ring of gas. The Cat's Eye Nebula has complex, nested shells of gas in brilliant blues and reds. They are fleeting on astronomical timescales. A planetary nebula lasts only about 10,000 years before the gas disperses into the surrounding interstellar medium and fades away. In the grand timeline of stellar evolution, a planetary nebula is a brief, quiet flourish at the end of a star's life. Let the image rest in your mind. A glowing shell of gas drifting slowly outward through space, lit by the last light of a dying star. Colors that have never been seen by human eyes in person. Structures too large to imagine unfolding in silence across thousands of years. At the center of the planetary nebula, after the outer layers have drifted away, what remains is the exposed core of the star. This object is called a white dwarf. A white dwarf is a remarkable thing. It is roughly the mass of the sun, sometimes a little less, squeezed into a volume, roughly the size of the Earth. It is extraordinarily dense. A teaspoon of white dwarf material would weigh several tons on Earth. The white dwarf is not powered by nuclear fusion anymore. The core is made of carbon and oxygen, and in a star of the sun's mass, the temperature and pressure are not high enough to fuse carbon. So the nuclear reactions have stopped. The white dwarf shines only from the residual heat that was built up over billions of years of nuclear burning. It is slowly, very slowly, cooling down, like an ember glowing after the fire has gone out. How long does a white dwarf take to cool? A very long time. White dwarfs cool extraordinarily slowly. A newly formed white dwarf might be very hot, tens of thousands of degrees, on its surface. Over billions of years, it gradually cools. But even after hundreds of billions of years, it will still be warm. After an almost incomprehensible stretch of time, perhaps a quadrillion years, or more, a white dwarf will cool to the point where it no longer emits significant visible light. At that point, it becomes a cold, dark, dense object called a black dwarf. But here's a fascinating fact. No black dwarfs are thought to exist yet. The universe is only about 13.8 billion years old, and that isn't long enough for any white dwarf to have cooled completely. Every white dwarf that has ever formed is still glowing, at least faintly. The oldest, coolest white dwarfs we can find are still around 4,000 degrees Celsius. Still warm, still slowly fading. There's something quietly touching about that. These ancient stellar remnants, the cores of dead suns still holding on to a little warmth after billions of years. White dwarfs can exist up to a certain mass. Above that mass, something different happens. The maximum mass a white dwarf can have is called the Chandrasekhar limit, after the Indian-American astrophysicist Subramanian Chandrasekhar, who calculated it in 1930 when he was just 19 years old. The Chandrasekhar limit is about 1.4 times the mass of the Sun. If a white dwarf somehow gains mass, perhaps by pulling gas from a companion star in a binary system, and its mass approaches 1.4 solar masses, something dramatic happens. The white dwarf can no longer support itself. It can't hold back gravity. What happens next depends on the specifics, but one common result is a thermonuclear explosion. A white dwarf that pushes past the Chandrasekhar limit can undergo a catastrophic runaway fusion reaction. The carbon in the white dwarf fuses rapidly and explosively, and the result is a Type Ia supernova, an explosion so bright it can outshine an entire galaxy. But we'll talk more about supernovae in a moment. For now, the main thing to know is this. For a star like the Sun, the end of the story is a white dwarf, a small, dense, slowly cooling remnant, peaceful in its way, still warm, still present, just no longer shining brightly. The Sun's life will not end with an explosion. It will end with a long, quiet fade. Just let that sit for a moment. The Sun's life, and the life of stars like it, ends not with a bang, but with a very, very slow dimming. A cooling, a long, patient fade into darkness. There's something almost restful about that. Let's take a moment here. We've covered a lot of ground. We've talked about how stars are born from clouds of gas, how they spend most of their lives quietly burning hydrogen into helium, how they expand into red giants when the hydrogen is exhausted, how they shed their outer layers and end up as white dwarfs. That's the story for medium-sized stars like the Sun. But stars come in many different sizes, and for larger stars, the story is very different. Take a breath. Notice how quiet it is where you are. Notice the stillness. The stars outside, if you could see them, right now are doing everything we've described at this very moment. Some are in their youth, just beginning to burn. Some are in their long, stable middle phase. Some are in the red giant phase, slowly swelling. Some are shedding their outer layers. Some are white dwarfs slowly cooling. All of these things are happening right now across the galaxy in profound silence. We're going to turn now to the more massive stars, the ones that don't end quietly, the ones that end in the most energetic explosions in the universe. But even those stories told slowly and gently can be calming, because they are old stories, ancient stories, and there's a kind of peace in understanding ancient things. For stars significantly more massive than the Sun, say, 8 times the mass of the Sun, or more the story of stellar death, is very different and more dramatic, but let's tell it slowly. A massive star lives fast, as we mentioned earlier. A star, 10 times the mass of the Sun, might only last 10 million years on the main sequence. A star, 30 times the mass, might last only a few million years. These are very short lives in stellar terms. When a massive star begins to run out of hydrogen in its core, it also expands. It also becomes a giant. In fact, it becomes a supergiant, even larger than a red giant. Stars called red supergiants can be hundreds of times the radius of the Sun. The star, Betelgeuse, which you can see in the night sky as the reddish shoulder of the constellation Orion, is a red supergiant. If you put Betelgeuse where our Sun is, its surface would extend out beyond the orbit of Jupiter. But a massive star doesn't stop at helium fusion. It has more gravity, more pressure, more temperature. After the helium in its core is exhausted, the carbon can fuse. After carbon comes neon. After neon comes oxygen. After oxygen comes silicon. Massive stars burn through a sequence of heavier and heavier elements, each phase shorter than the last. The silicon burning phase, the last stage of nuclear fusion, in a massive star, lasts only a few days. At the end of silicon burning, the core becomes iron. And iron is where it all stops. Iron is special in nuclear physics. Fusing iron nuclei together does not release energy. It requires energy, and breaking iron apart also requires energy. Iron sits at the bottom of the nuclear energy landscape. It is the most stable nucleus. When a massive star's core becomes iron, nuclear fusion stops. There is no more energy to be extracted. Gravity takes over. The iron core of a massive star grows over the final days of silicon burning. Iron nuclei are added to it constantly, but iron can't provide energy, so the core has no energy source to resist gravity. The iron core is held up briefly by something called electron degeneracy pressure. This is a quantum mechanical effect, the pressure that electrons exert simply because quantum mechanics doesn't allow them to occupy the same quantum state. It's the same thing that holds up white dwarfs, but there's a limit to how much electron degeneracy pressure can resist. And that limit is similar to the Chandrasekhar limit, about 1.4 solar masses. When the iron core reaches about 1.4 solar masses, electron degeneracy pressure can no longer hold it up, and the core collapses. Not slowly, not over millions of years, over fractions of a second. The iron core, which was perhaps the size of Earth, collapses to a ball roughly 20 kilometers across, the size of a city, in less than a second. During this collapse, the electrons and protons in the iron nuclei are forced together, forming neutrons. The iron core becomes a ball of neutrons. This object is called a neutron star. The collapse is so sudden and so extreme that the infalling gas of the star's outer layers actually bounces off the newly formed neutron star, like a wave hitting a wall, and that bounce sends a shockwave outward through the star. The result is a core collapse supernova. A supernova is, by some measures, the most energetic event in the universe after the Big Bang itself. In the fraction of a second when the core collapses, the energy released is roughly equivalent to the energy our Sun will emit over its entire 10 billion year lifetime. Most of that energy, about 99% of it, is carried away by tiny particles called neutrinos. Neutrinos interact so weakly with matter that they pass right through the entire star almost instantaneously, carrying the energy away into space. The remaining 1% goes into the explosion, and that 1% is still enough to blow the entire outer envelope of the star apart at speeds of thousands to tens of thousands of kilometers per second. and to briefly make the explosion as bright as billions of stars combined. For a few weeks, a supernova can outshine an entire galaxy of hundreds of billions of stars. Imagine that for a moment. One dying star, briefly shining as brightly as everything else in the galaxy combined. Then slowly it fades, over weeks, over months, until only the remnants are left. Supernovae are important for another reason, though. During the explosion, the intense neutron flux creates elements heavier than iron. Gold, silver, platinum, uranium. Many of the heavy elements in your jewelry and in the Earth's crust were made in supernova explosions billions of years ago and scattered across space before gathering into our solar system. The gold in any ring you might be wearing was forged in the death throes of a star. Let that image settle quietly. The gold on Earth, the silver, the platinum, these are stellar debris, scattered by ancient explosions, gathered by gravity into our solar system. And now here, solid and cool and familiar. Ancient stellar fire, now cold and quiet. After a core collapse supernova, two things remain. The first is the supernova remnant, the expanding shell of gas and dust that used to be the outer layers of the star. This shell expands outward for thousands of years, eventually dissipating into the interstellar medium. Supernova remnants are beautiful objects. The Crab Nebula in the constellation Taurus is a famous example. It's the remnant of a supernova that was observed by Chinese astronomers in the year 1054. Today, it's an expanding cloud of glowing filaments, about 11 light-years across, still expanding. The second thing left after a supernova is the compact remnant at the center. For most core collapse supernovae, the central remnant is a neutron star. A neutron star is one of the most extreme objects in the universe. It has a mass of 1 to 3 times the Sun, all squeezed into a ball about 20 kilometers across. A teaspoon of neutron star material would weigh around 1 billion tons on Earth. The density is comparable to having the mass of Mount Everest squeezed into the volume of a sugar cube. Neutron stars have some extraordinary properties. They spin very fast, often hundreds of times per second. They have magnetic fields billions or trillions of times stronger than Earth's. Some of them emit beams of radio waves from their magnetic poles, and as they spin, these beams sweep across space like cosmic lighthouses. When those beams point toward Earth, we detect regular pulses of radio waves. These objects are called pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student. The signal was so regular and unexpected that it was briefly nicknamed LGM, one for Little Green Men. Of course, it turned out to be natural, but the regularity of pulsars remains remarkable. Some of them keep time more accurately than the best atomic clocks we have on Earth. A neutron star just spins. Slowly, over millions of years, it loses energy. Its spin slows. Its magnetic field weakens. Eventually, it becomes just a cold, dense, spinning ball of neutrons in the dark. Neither bright nor violent, just existing. Very old, very dense, very quiet. For the most massive stars, those with perhaps 25 or more times the mass of the Sun, the central remnant after a supernova may be too massive for even neutron degeneracy pressure to support. When that happens, the core continues to collapse. There is nothing left to stop it. The matter collapses to a point of infinite density, or at least a region so small and dense that our physics breaks down trying to describe it. And the result is a black hole. A black hole is a region of space where gravity is so strong that nothing can escape, not even light. The boundary of a black hole is called the event horizon. Anything that crosses the event horizon is trapped forever. Even a photon of light, traveling at 300,000 kilometers per second, cannot escape. If it crosses the the event horizon. From the outside, a black hole appears as nothing, a region of darkness where the stars behind it are bent and distorted by the intense gravity. It doesn't shine. It doesn't glow. It's simply an absence. The idea of a black hole is strange and a little hard to visualize. But let's try a gentle way of thinking about it. The surface of the Earth has an escape velocity, the speed you need to travel to escape. Earth's gravity. For Earth, it's about 11 kilometers per second. The Moon has a lower escape velocity because it's less massive. A neutron star has a much higher escape velocity, a significant fraction of the speed of light. A black hole is simply an object whose escape velocity has reached and exceeded the speed of light. Since nothing can travel faster than light, nothing can escape. It's not a hole in space in a literal sense. It's a region where gravity is so overwhelmingly dominant that space-time itself curves all the way back around, creating a one-way boundary. Inside that boundary, time itself behaves in ways that no longer resemble what we experience in everyday life. These are very deep waters in physics. Tonight, we don't need to go all the way in. Just know that black holes exist. They're real. We have observed them, and they are the endpoints of the most massive stars' lives. Our galaxy, the Milky Way, is about 10 billion years old. In that time, billions of stars have lived and died. All those stellar deaths have left behind remnants. White dwarfs, neutron stars, black holes scattered throughout the galaxy like the remnants of ancient fires. It's estimated that there are roughly 10 billion white dwarfs in the Milky Way, about 1 billion neutron stars, and perhaps 100 million black holes formed from stellar collapse. These objects are mostly dark and hard to detect, but they're out there, drifting quietly through the galaxy. The cold, dense remnants of stars that burned billions of years ago. The white dwarfs are the most numerous, and in some ways the most poignant. Each one is the core of a star that once burned brightly, perhaps as brightly as the sun, and now exists as a slowly cooling ember, still warm but fading. The oldest white dwarfs we found are about 11 or 12 billion years old. They've been cooling for almost as long as the Milky Way has existed, and they're still warm, still there. There's something comforting about that, in a way. Even after the fire is gone, the warmth persists for a very, very long time. Let's just rest here for a moment. We've been through a lot of stellar history. We started with clouds of gas. We watched them collapse and ignite. We followed a star through its long, quiet, main sequence life. We saw it swell into a red giant, shed its outer layers, and leave behind a white dwarf. For more massive stars, we saw the layered core, the iron heart, the collapse, the supernova, and the remnant neutron star or black hole. All of these things are happening in the universe right now, slowly, silently, across unimaginable distances. The night sky, if you could see it through the walls, is not a static painting. It is a living process. Stars being born, stars burning, stars dying, each one following a path determined largely by its mass, and all of it happening over timescales that make human history look like a single heartbeat. Just breathe. The universe is very old and very patient. It has been doing these things for almost 14 billion years. It will continue doing them for trillions more. There is no hurry. There never is. Now let's think about why stellar death matters. Not just as an event, but as part of the larger story of the universe. When stars die, whether quietly through a planetary nebula or explosively through a supernova, they return material to the galaxy. The gas and dust they shed, enriched with elements forged in stellar cores, spreads out into the interstellar medium. Over time, this enriched material mixes with the original hydrogen and helium leftover from the Big Bang. And when new clouds condense and new stars form, they form from this enriched material. The first stars in the universe formed from almost pure hydrogen and helium, the elements created in the Big Bang. There were no heavier elements because no stars had yet lived and died to create them. Those first stars, called population 3 stars, burned ferociously. They were probably very massive, very bright, very hot, and they died quickly in enormous supernovae, scattering the first heavy elements into the universe. The next generation of stars, population 2 stars, formed from gas enriched with those first heavy elements, and so on. Each generation of stars enriches the galaxy a little more, adds more carbon, more oxygen, more silicon, more iron. Our Sun is a population 1 star, a relatively late generation, formed from gas enriched by many generations of previous stars. And we are made of that enriched material. The oxygen in your body, the carbon, the nitrogen, the calcium, the iron in your blood, all of it forged in the cores and death explosions of stars that came before our Sun. Stars that lived and burned and died, scattering their contents across the galaxy, so that eventually some of those contents could become you. You are the universe's way of using dead stars to think about dead stars. That thought can float gently in your mind. Let's talk about some specific stars that are near the end of their lives. We don't have to go far. Many of the stars visible to the naked eye in the night sky are old evolved stars. Betelgeuse, as we mentioned, is a red supergiant in the constellation Orion. It's one of the largest stars visible to the naked eye. It is hundreds of times the radius of the Sun, and it has a reddish-orange color because its surface is relatively cool for a star about 3,500 degrees Celsius. Betelgeuse is expected to explode as a supernova at some point. In stellar terms, at some point could mean tomorrow, or it could mean 100,000 years from now. We don't know precisely. When it does explode, it will be visible from Earth during the daytime. It will be brighter than a full moon for weeks. It will be a remarkable sight, but it will also be far enough away, about 700 light years, that there is no danger to Earth. The supernova will be a display, not a threat. Antares, in the constellation Scorpius, is another red supergiant. Its name is sometimes interpreted to mean rival of Mars because of its reddish color. Antares is even larger than Betelgeuse, one of the largest known stars. Both Betelgeuse and Antares are near the end of their lives by stellar standards. Both will someday explode. Both are remarkable to look at if you can find them. Aldebaran, the bright star in the constellation Taurus, is a red giant, past the main sequence, swelling in its old age, but not yet close to explosion. Arcturus, the brightest star in the northern celestial hemisphere, is also a red giant, cooler and larger than the Sun in the late stages of its life. These old reddish stars are scattered throughout the sky. You've probably seen them many times without knowing what they were. Steady, warm, slightly reddish points of light, each one a sun in its old age. Some stars in their old age don't burn steadily. They pulsate, they expand and contract rhythmically, like a slow, deep breathing. These are called variable stars, and there are several types. One famous type is the Cepheid variable, named after the star, Delta Cephei, in the constellation Cepheus. Cepheids are giant stars that pulsate with very regular periods, usually between 1 and about 100 days. The remarkable thing about Cepheids is that their period of pulsation is directly related to their actual luminosity, how much light they emit. So if you observe a Cepheid and measure its period, you can calculate how bright it actually is. Then comparing that to how bright it appears from Earth, you can calculate its distance. Cepheid variables became one of the most important tools in astronomy for measuring distances across the universe. Edwin Hubble used them in the 1920s to measure the distances to other galaxies and discovered that the universe is expanding. Another type of variable star is the Mira variable, named after the star Mira in the constellation Cetus. Mira variables are red giant stars in the late stages of their lives. The asymptotic giant branch stars we talked about earlier, they pulsate over periods of months to years, and their brightness can change dramatically. Mira itself varies from being easily visible to the naked eye to being completely invisible without a telescope over a period of about 332 days. These pulsating stars are essentially in a state of instability. The balance between gravity and energy has broken down just enough that the star oscillates around that balance, compressed too far, and the energy pushes it back out, expand too far, and gravity pulls it back in. Like a pendulum, like breathing, the star doesn't explode. It just breathes slowly for thousands of years as it approaches the end. So far, we've been talking mostly about single stars, stars that live and die alone. But about half of all stars are in binary systems, two stars orbiting each other, sometimes close enough to interact. When one of the stars in a binary system runs out of fuel and expands into a red giant, it can interact with its companion in interesting ways. If the two stars are close enough, the expanding red giant can actually transfer material to its companion. Gas from the outer layers of the giant falls onto the companion star, or onto a white dwarf that the companion has already become. When material falls onto a white dwarf, it accumulates on the surface. Over time, this accumulated hydrogen reaches a critical temperature and pressure and undergoes a rapid fusion reaction. The result is a nova, a sudden brightening of the white dwarf as the accumulated hydrogen burns off. Not a supernova. A nova, less energetic, and usually the white dwarf survives. The cycle can repeat as more material accumulates and burns off again. If, however, the white dwarf accumulates enough material to push its mass toward the Chandrasekhar limit, 1.4 solar masses, it can undergo a much more catastrophic event. The carbon in the white dwarf ignites all at once in a runaway thermonuclear explosion. This is the type Ia supernova we mentioned earlier. Unlike a core collapse supernova, a type Ia leaves nothing behind. The white dwarf is completely destroyed. All its mass is blown outward in the explosion. These type Ia supernovae were used in the 1990s to measure distances across the universe. And they led to the discovery that the expansion of the universe is accelerating, driven by a mysterious force called dark energy. So a white dwarf exploding in a binary system 3 billion years ago far across the universe provided one of the most important astronomical discoveries of the 20th century. The universe has a way of making connections across time and space that are hard to fully appreciate. An ancient stellar remnant, an explosion no one witnessed, light traveling 3 billion years, and a team of astronomers in the 1990s finding it in their data and realizing the universe is not what they thought. Let's pause again and feel the quiet. All of these events, the births of stars, their long lives, their expansions, their shedding of gas, their explosions, all of these things happen in absolute silence. Space is not quite a perfect vacuum, but it is close enough to one that sound cannot travel through it. There are no sound waves crossing the interstellar medium. Supernovae are catastrophic explosions, but they are completely silent from a distance. The universe is profoundly quiet. If you were floating in space at a safe distance from a supernova, you would see the light, a brilliant expanding ball of illuminated gas. You would feel the radiation perhaps pressing gently against you, but you would hear nothing, just silence, the same silence that fills all of space. The same silence that has filled space for 14 billion years. While all of this has been happening, there is something very calming about that silence. All the drama of stellar birth and death, all the immensity of it, happening in perfect, complete silence across the galaxy. You are in that galaxy, and on a quiet night, with the lights off, you can begin to feel the edges of that silence coming in. Let's think for a moment about the very far future of stars. Right now, the universe is in what might be called the stelliferous era, the age of stars. Stars are forming. Stars are shining. The galaxy is bright with stellar fire. But this era will not last forever. Over time, the gas in galaxies gets used up. Some of it forms stars, which burn it into heavier elements. Some of those heavier elements end up locked in stellar remnants, white dwarfs, neutron stars, black holes, and never return to gas. Gradually, the supply of fresh hydrogen available to form new stars decreases. In a very rough sense, star formation will continue for another trillion years or so. Beyond that, the gas will be mostly used up, and new star formation will essentially stop. After that, only long-lived stars will remain. The small, dim red dwarf stars that burn their fuel so slowly they can last 100 billion years or more. These stars will continue to shine for trillions upon trillions of years, long after the sun, and all stars like it have faded to white dwarfs. The universe in the far future will be a dimmer, quieter place, dominated by small, red, slowly cooling suns with their families of planets, if they have them, drifting through a vast and mostly dark galaxy. Eventually, even the red dwarfs will exhaust their fuel. They will not become red giants. They're too small for that. They will simply burn down to helium white dwarfs, dim, small, slowly cooling. And after that, after all the stars have gone out, trillions upon trillions of years from now, the universe will enter what cosmologists call the degenerate era, a time when the only luminous objects are the rare nova or the occasional collision of white dwarfs. A very dark, very quiet time. Then, after an almost incomprehensible span of time, even the white dwarfs will cool to black dwarfs. And even further out, the neutron stars and black holes will eventually evaporate through processes we barely understand yet. Hawking radiation, in the case of black holes. The universe, in the most extreme long run, becomes cold and dark and empty. But that is so far in the future that it has no emotional weight to carry. It's not sad. It's simply the logical unfolding of physics, playing out over timescales that no human mind can truly hold. Right now, the universe is young. The stars are shining, and there is beauty in every direction. There's one more phenomenon worth mentioning quietly. When two neutron stars orbit each other closely, they slowly spiral inward. As they orbit, they emit gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein's general theory of relativity. These gravitational waves carry energy away from the system. And as energy is lost, the two neutron stars move closer together. Closer and closer over millions of years, until they collide. When two neutron stars collide, the result is called a kilonova, a different kind of explosion from a supernova, but still enormously energetic. And this process is thought to be responsible for creating many of the heaviest elements, including gold, platinum, and uranium. In 2017, a kilonova was observed for the first time by multiple telescopes simultaneously, along with the gravitational wave signal detected by the LIGO Observatory. It was one of the most remarkable moments in modern astronomy. The universe observed in a new way, in multiple wavelengths of light, and in gravitational waves at the same time. Gravitational waves are so subtle that they pass through everything. Right now, gravitational waves from distant events are passing through the Earth, through your body, through everything. They stretch and compress space by amounts so tiny that they're almost unimaginably small, smaller than 1,000th of the width of a proton. They're everywhere, and they carry information about the universe's most extreme events, quietly passing through. Let's take a gentle detour through nuclear physics, just the surface of it, the part that's relevant to understanding why stars die. The universe started with hydrogen and helium. That's essentially all there was after the Big Bang. Hydrogen, 1 proton, 1 electron. Helium, 2 protons, 2 neutrons, 2 electrons, and trace amounts of lithium. Everything else, every other element on the periodic table, was made later, mostly in stars. Nuclear fusion is the process of combining smaller nuclei into larger ones. When you fuse hydrogen into helium, you release energy. When you fuse helium into carbon, you release energy. When you fuse carbon and other lighter elements into heavier ones, you release energy. But this only works up to iron. Iron, as we said, sits at the bottom of the nuclear energy landscape. Building nuclei bigger than iron takes energy, rather than releasing it. So stellar fusion creates elements up to iron. Beyond iron, other processes are needed. Some heavy elements are created by the slow neutron capture process, called the S process, which happens in red giant stars over long periods of time. Neutrons are gradually added to lighter nuclei, and they beta decay into heavier elements. Other heavy elements are created by the rapid neutron capture process, called the R process, which requires extremely high fluxes of neutrons. For a long time, scientists debated where the R process happens. Core collapse supernovae were the leading candidate, but the kilonova observations of 2017 suggested that neutron-star mergers may actually be the primary site. So the heavy elements in the universe, all the elements heavier than iron, come from stellar death events, some from supernovae, some from neutron-star mergers, all of them catastrophic, all of them ancient. The gold standard, so to speak, for heavy element production is the death of stars. Sometimes it helps to try to feel the scale of what we're talking about, even if we can't truly comprehend it. The Sun is about 1.4 million kilometers in diameter. That's about 109 times the diameter of the Earth. If the Earth were a grape, the Sun would be about the size of a beach ball. But the Sun is just an average-sized star. Betelgeuse is about 1,000 times the diameter of the Sun. If the Sun were a grain of sand, Betelgeuse would be about a meter across. And that's just the star itself. The planetary nebulae that surround dying stars extend for light years, trillions of kilometers. The distances between stars are even more staggering. The nearest star to the Sun is Proxima Centauri, about 4.24 light-years away. A light year is about 9.46 trillion kilometers. That's roughly 40 trillion kilometers to Proxima Centauri. If you could drive a car at highway speed without stopping, it would take about 40 million years to reach Proxima Centauri. The Milky Way galaxy is about 100,000 light-years across, and it contains something like 200 to 400 billion stars. These numbers are too large to hold in the mind, and that's fine. The goal isn't to comprehend them. The goal is just to let them wash over you like water, to feel the vastness of things. The universe is enormously, almost impossibly large, and yet it is also very quiet, and from our point of view on this small planet, very distant and very still. One of the most remarkable things about stellar physics, and about physics in general, is that the same rules apply everywhere. The nuclear physics that governs fusion in the Sun is the same nuclear physics that governs fusion in a star a billion light-years away. The same rules, the same constants, the same processes. Gravity works the same way in our galaxy as it does in galaxies on the other side of the visible universe. The periodic table is the same everywhere. Hydrogen is hydrogen. Carbon is carbon. Iron is iron. The same elements, made by the same processes, following the same rules. This universality is, in a quiet way, one of the most profound things we know. The universe is lawful, not in a moral sense, but in a physical sense. The same rules apply everywhere, always. And because of that, we can understand distant stars, objects we have never and will never visit, purely by measuring the light they emit. We can know what they're made of, how hot they are, how fast they're moving, how far away they are, whether they have planets, all from light, ancient light, traveling across space. And those same rules mean that the story we've told tonight, the birth of stars, their long lives, their deaths, is not just the story of a few stars we've studied. It's the story of every star that has ever existed and every star that ever will exist. The specific details vary. The masses are different. The compositions are different. The lifetimes are different. But the underlying story is the same. Let's think about time for a moment. The universe is about 13.8 billion years old. The sun has been burning for 4.6 billion years. Life on Earth has existed for about 3.8 billion years. Complex animal life has existed for maybe 600 million years. Humans have existed for perhaps 300,000 years. All of recorded human history covers maybe 5,000 to 10,000 years. The sun will continue to burn for another 5 billion years. On the scale of the sun's life, all of human civilization is less than 1/1,000,000% of the total. That's not a depressing thought. It's a calming one. Human civilizations rise and fall. Technologies disappear and are forgotten. Languages are spoken and die out. Empires are built and crumbled. And all the while the sun burns on. Steady, patient, unhurried. The sun was burning when the first bacteria appeared in the ocean. It was burning when the first fish crawled onto land. It was burning when the dinosaurs walked. It was burning when the first humans looked up at it and felt warm. And it will be burning long after. There's a deep calm in that perspective. All the urgency of daily life, the deadlines and decisions and worries. They're real, but they exist inside a much larger, quieter frame. The stars don't hurry. We've talked about stars being born in nebulae and dying in nebulae. Let's spend a moment just appreciating these clouds. A nebula is simply a cloud of gas and dust in space. The word comes from the Latin word for cloud or mist. Some nebulae are star-forming regions, active nurseries where new stars are condensing out of the gas. The Orion Nebula is a famous example. You can see it with the naked eye as a faint smudge in the sword of Orion. With a telescope, it resolves into a dramatic cloud of gas and dust lit by young, hot stars forming within it. Other nebulae are the remnants of stellar death, the planetary nebulae surrounding dying, sun-like stars, the supernova remnants left by exploding, massive stars. And some nebulae are neither. They're just clouds of gas and dust that haven't yet formed stars, or that were illuminated by nearby stars. All of them are beautiful in different ways. The diffuse glow of a reflection nebula scattering blue starlight. The structured filaments of a supernova remnant. The nested shells of a planetary nebula. The dark, dusty silhouettes of a molecular cloud against a bright background. Astronomers have photographed thousands of these objects. The images are extraordinary. They're the visual side of the story we've been telling tonight. If you've ever seen images from the Hubble Space Telescope, or from the newer James Webb Space Telescope, you've seen these things, vast and colorful and impossibly detailed. The images show things our naked eyes never could. Ultraviolet light, translated to blue infrared light, translated to red, the structures of gas and dust made visible through advanced optics and detectors. There's something worth sitting with when you have the chance. But for now, in the dark, the imagined versions are enough. Stars come in many types, and astronomers have developed a system for classifying them. The classification system is based on a star's temperature, which correlates with its color. Hot stars are blue or blue-white. Cooler stars are yellow, orange, or red. The spectral types from hottest to coolest are O, B, F, G, K, and M. There's an old mnemonic for remembering this. O, be a fine guy/girl. Kiss me. O stars are the hottest and most massive. The brilliant blue giants and supergiants that live fast and die young. They can be tens or even hundreds of times the mass of the sun, and they burn at surface temperatures above 30,000 degrees Celsius. B stars are slightly cooler, still very hot and blue-white. Rigel, the bright blue star in Orion, is a B supergiant. A stars are white or blue-white. Sirius, the brightest star in the night sky, is an A star. F and G stars are yellow-white to yellow. Our sun is a G star with a surface temperature of about 5,500 degrees Celsius. K stars are orange. Arcturus and Aldebaran are K giants. M stars are the coolest and most common, red dwarfs and red giants. Betelgeuse and Antares are M supergiants. The vast majority of stars, something like 70%, are M stars, red dwarfs, small, cool, dim, and enormously long-lived. Bright O and B stars are rare, even though they're the ones we're most likely to notice in the night sky, because they're so luminous. The variety is wonderful when you think about it. Stars that burn blue-white and fierce for a few million years. Stars that glow orange and steady for tens of billions. Stars that burn dim and red for trillions. All of them following the same underlying physics. All of them on the same long road from cloud to remnant. Astronomers have a wonderful tool for visualizing stellar evolution: the HERTZSPRUNG-RUSSELL diagram. The HR diagram, as it's called, plots stars on a graph. On one axis is temperature, or spectral type. On the other axis is luminosity, how much light a star emits. When you plot thousands of stars on this diagram, a beautiful pattern emerges. Most stars fall along a diagonal band stretching from the upper left, hot and bright, to the lower right, cool and dim. This band is called the main sequence. The main sequence is exactly what it sounds like: the sequence of stars that are in their main stable phase burning hydrogen in their cores. The Sun sits roughly in the middle of the main sequence. But off to the right and above the main sequence there are the giants and supergiants, cool but luminous. These are the evolved stars, the ones that have left the main sequence and are in later stages of their lives. And down in the lower left, small and hot and dim, are the white dwarfs. The HR diagram tells the story of stellar evolution in a visual way. A star spends most of its life as a dot on the main sequence. Then, as it runs out of hydrogen, it moves off to the right and upward, becoming a giant. Then, as it sheds its outer layers, it moves leftward and downward, becoming a white dwarf, hot at first, then cooling toward the right as it fades. The whole life of a star sketched out on a simple graph. Watching a theoretical stellar evolution track move across an HR diagram is one of the genuinely elegant things in astrophysics. A single point moving slowly across the diagram over billions of years, tracing the arc of a stellar life. There's a quiet beauty to it. Let's think for a moment about the people who study all of this. Astronomers and astrophysicists spend their careers trying to understand stars and galaxies and the universe. Not because it has immediate practical applications, though sometimes it does, but because the questions are fascinating. What happens inside a dying star? How do supernovae work in detail? What creates the structures of planetary nebulae? What are the properties of neutron stars? How do black holes grow evolve? These are questions that humans have only been able to begin answering in the last century or so. 100 years ago, we didn't know that other galaxies existed. We didn't know the age of the universe. We didn't know how stars powered themselves. The pace of discovery in astrophysics over the past century has been remarkable, and yet the questions keep coming. Every answer opens new questions. The universe is patient about revealing its secrets. Most of what we know about stars comes from analyzing their light. When light passes through a prism, it spreads into a rainbow of colors, a spectrum. Different elements absorb and emit specific wavelengths of light, creating distinctive patterns called spectral lines. By analyzing the spectral lines in a star's light, astronomers can determine what elements the star contains, how hot it is, how fast it's moving toward or away from us, and many other properties. It's a remarkable fact that you can learn so much about an object from nothing, but the light it emits. The people who study these spectra, who analyze these data, who build the theories and test them against observations, they spend their days thinking about ancient and distant things, about nuclear reactions in stellar cores, about gas clouds collapsing, about the last seconds before a supernova. It's a quiet kind of work in many ways. Patient, painstaking, done in offices and observatories and cafeterias over many years. There is, of course, a human dimension to all of this. Stars have been part of human experience for as long as humans have existed. Before writing, before history, people looked up and saw the stars and wondered about them. They used them for navigation. They used them to mark seasons. They built stories around them, constellations, myths, cosmologies. Every human culture that has ever existed has had something to say about the stars. There's a reason stars feel significant to us. They're constant in a human sense. The stars you see tonight are in most cases the same stars your great-great-grandparents saw. The same stars that people have seen for thousands of years. In a world of constant change, the night sky offers something stable. Something that was there before you were born and will be there after you're gone. And yet we now know that the stars are not actually eternal. They are born, they burn, they die. Even the most long-lived red dwarfs will someday exhaust their fuel. But the knowledge that stars die doesn't diminish them. If anything, it makes them more meaningful. A star is a process, a long, slow, glorious process. And like all processes, it has a beginning and an end. What fills the time between beginning and end is billions of years of light, a steady pouring forth of energy into the surrounding darkness. That seems worth something. On a clear night away from city lights, the sky is full, not just with the handful of stars you can see from a lit suburb, not the handful of very bright stars that pierce through light pollution. Away from the lights, the sky fills with thousands of stars. Then the Milky Way itself becomes visible, a band of light stretching across the sky, the blurred glow of hundreds of billions of stars too distant to see individually. Looking at the Milky Way on a clear night is one of the genuine experiences that is very hard to describe to someone who hasn't seen it. The Milky Way is our galaxy seen edge-on from inside. The band of light you see is the dense central disk of the galaxy. Our solar system sits out toward the edge, about 26,000 light-years from the center. When you look toward the center of the Milky Way, in the direction of the constellation Sagittarius, you're looking toward the densest part of our galaxy, toward the greatest concentration of stars. And at the very center, there is a supermassive black hole called Sagittarius A*, with a mass of about 4 million times the mass of the Sun. It doesn't do anything dramatic on human timescales. It's surrounded by a relatively sparse region of space at the moment. It just sits there at the center of our galaxy. Massive and quiet, there are things to see in every direction in the night night sky. Old things, immense things, quietly wonderful things. And most of us, most of the time, never look up. We are nearing the end of our journey tonight. Let's let the information settle slowly. You've learned about how stars are born from collapsing gas clouds, how they spend billions of years burning hydrogen into helium, how they swell into red giants when the hydrogen is exhausted, how medium-sized stars shed their outer layers and leave behind white dwarfs, how massive stars build layers of heavier elements until their iron cores collapse and trigger supernovae, how the most massive stars leave behind neutron stars or black holes, and how through all of this dying, the universe is enriched. The elements created in stellar cores are scattered across space to be gathered into new stars, new planets, new forms of chemistry. This is the cycle of stellar matter. Not eternal life, but something meaningful nonetheless. Matter and energy cycling through different forms over billions of years. The hydrogen in a star might spend 1 billion years as a gas cloud, then 10 billion years inside a star. Then after the star's death, it might drift as interstellar gas for millions of years before being swept up into a new star system. It might end up in a planet, or in an ocean, or eventually in a living thing. Matter doesn't disappear. It transforms. It moves through different forms, each form lasting a very long time before giving way to the next. There's a kind of peace in that continuity. The atoms in your body will outlast you by billions of years. They will go on after you into forms you can't predict, into other stars perhaps, into other planets, into other forms of life if life persists. The story doesn't end. It continues, in ways that are beyond our ability to follow. Let's come back to the beginning. We started with you, settling in for the night. The lights low, the room quiet. Outside, if the sky is clear, there are stars. And now, you know a little more about them than you did before. You know that each one is a process, a long, slow nuclear process that began as a cloud and will end as a remnant. You know that the elements in your body came from stellar cores. You know that some of those stars visible tonight are in their youth, some in their middle age, some in old age. You know that the universe is old and patient and quiet, that things happen on timescales that dwarf human experience, that stars are born and stars die, and through that dying, the universe is enriched. There's nothing urgent here, nothing to worry about. The stars are stable. The sun is stable. It has 5 billion years left. Whatever worries are real in your life, they're real, but they exist inside this larger quiet. The universe has been here for almost 14 billion years. It will be here for trillions more. And through all of it, the stars will do what they do. Quietly, steadily, without hurry. Let your body settle. Let your breathing slow. The information we've covered tonight, it doesn't need to be held tightly. Let it drift, like gas in a nebula, slowly settling. There's one more thing to say before we close. The universe, for all its immensity, is mostly quiet. Between the stars, there is almost nothing. Not quite nothing. There are a few atoms of gas per cubic centimeter of space on average. There is radiation, the cosmic microwave background, the faint afterglow of the Big Bang itself, still washing through the universe at a temperature just a few degrees above absolute zero. But there is no air to carry sound, no ground to transmit vibrations, just the almost nothing of intergalactic space. The deepest quiet in our experience is nothing compared to the quiet of deep space. And yet, in that quiet, all of this is happening. Stars condensing from clouds, nuclear fires burning in stellar cores, gas streaming from dying stars, supernovae lighting up galaxies, gravitational waves rippling through space-time, all of it in silence. When you lie in the quiet of a room at night, and the world outside has gone still, you're brushing up against something like that cosmic silence. Not the same, not nearly the same, but a faint human echo of it. The world quiets, the noise fades, and in that quiet, there's just the room, just the breath, just the sense of being a living thing in a very large and very old universe. That's enough. That's more than enough. Let's return one more time to the elements. The chemical elements that stars create and scatter. The Big Bang created hydrogen, mostly hydrogen, about 75% by mass, and helium, about 25%. Everything else was made later. The first stars fused hydrogen and helium into slightly heavier elements, carbon, nitrogen, oxygen. When they died, those elements were scattered. Each generation of stars has contributed more. More carbon, more oxygen, more silicon and sulfur and iron. The Earth formed about 4.6 billion years ago from a cloud of gas and dust enriched by many generations of previous stars. That enriched cloud contained not just hydrogen and helium, but all the heavier elements, the ones needed for rocky planets, for chemistry, for biology. The Earth is made of stellar remnants: iron, silicon, oxygen, magnesium, nickel, and life on Earth uses the same elements that stars made. Carbon, the backbone of organic molecules. Oxygen, which life learned to breathe. Nitrogen, which is in every protein and every strand of DNA. Phosphorus, which carries the energy currency of cells. Sulfur, which helps proteins fold. These elements didn't have to exist. They exist because stars lived and died, because in their deaths they scattered what they had made. The universe produced life, at least here on this planet, through the vehicle of stellar death. Stars had to die so that we could exist. That's not a sad statement. It's a quietly extraordinary one. If you could see the sky right now, if it were clear and dark, and you were outside, here's what some of those lights are doing. That bright star in the west, it might be Venus, actually. Not a star at all, but a planet, reflecting sunlight. But the other lights, the smaller, steadier ones, those are stars. Some of them are main sequence stars like the sun, quietly burning, balanced, steady. Some of them are red giants, old stars past their prime, swelling slowly. In some distant planetary system, perhaps something has already been consumed by the expanding star. Some of them are very young, massive blue-white stars burning brilliantly for their short time. Some of what you see might not even exist anymore. If a star is 1,000 light years away, the light you see left it 1,000 years ago. The star might have died since then, and you wouldn't know yet. The news hasn't arrived. You're always looking into the past when you look at the stars. The nearest star's light is 4 years old. A star across the galaxy is 100,000 years old when you see it. The farthest galaxies we can see with the best telescopes show us objects as they were over 13 billion years ago, when the universe was young. The night sky is a kind of time machine, a window into different depths of the past, all visible simultaneously. It's a strange and beautiful thing. Stars are not always born alone. Often many stars form together from the same cloud of gas. These groups are called star clusters, and they are some of the most beautiful objects in the sky. There are two main kinds of star clusters. Open clusters are loose, irregular groups of a few hundred to a few thousand stars. They're usually found in the disk of the galaxy. The Pleiades, the Seven Sisters, are a famous open cluster. You can see them with the naked eye in the constellation. Taurus, a small group of blue-white stars clustered together. In dark skies, you can make out 6 or 7 individual stars. With binoculars, dozens more come into view. The Pleiades are relatively young as star clusters go, about 100 million years old. The bright blue stars in the cluster are young, massive, and hot, still in their energetic youth. They won't last long in stellar terms. perhaps another 100 million years before the most massive ones explode. Globular clusters are different. They are dense, roughly spherical collections of hundreds of thousands to millions of stars, all packed tightly together. They orbit the outer regions of galaxies like satellites. The Milky Way has about 150 known globular clusters. Globular clusters are very old, most formed in the early universe, more than 10 billion years ago. The stars inside them are ancient. They have long since passed through their main sequence lives, and the most massive ones are long dead. Looking at a globular cluster is like looking at a population of ancient stars. The bright stars you see in a globular cluster today are the red giants, the sun-like stars that have evolved off the main sequence. The main sequence itself in a globular cluster only extends partway up. The upper part, where young blue massive stars would be, is empty. Those stars burned out billions of years ago. There is something very peaceful about globular clusters. Spherical, dense, billions of years old, drifting slowly in the outer halo of the galaxy. Their most dramatic events, the supernovae of their massive stars, all happened long, long ago. Now they just drift, slowly orbiting the galaxy. They're ancient stars burning quietly in the dark. Some of those stars might have planets, and some of those planets might have had life billions of years ago in the early universe. We don't know. We may never know, but it's a quiet thought to sit with. Everything we know about stars we've learned from light, not from visiting them, not from sending probes, just from the light that reaches us across space. And that light, it turns out, contains an enormous amount of information. When starlight passes through a prism or through a diffraction grating, a surface with very fine lines ruled across it, it spreads into a spectrum of colors, a rainbow. But if you look at that spectrum very carefully, you see something besides the colors. You see dark lines, specific wavelengths where the light is missing. These are called absorption lines or spectral lines. Each element absorbs light at specific characteristic wavelengths. Hydrogen absorbs at certain wavelengths, helium at others, sodium at others, iron at others. Every element has its own fingerprint in the spectrum. By analyzing the pattern of lines in a star's spectrum, astronomers can determine what elements the star contains and in what quantities. This technique is called spectroscopy, and it is the foundation of almost everything we know about the chemical composition of stars. The sun's spectrum has thousands of absorption lines. Each line identifies a specific element in the sun's outer layers, the layer through which the light passes on its way out. From these lines we know that the sun is made mostly of hydrogen with a substantial amount of helium and small, but detectable amounts of many other elements: oxygen, carbon, nitrogen, silicon, magnesium, iron, and more. Spectroscopy also tells us about motion. When a source of light moves toward you, the waves are compressed. The light is shifted toward the blue end of the spectrum. When a source moves away from you, the waves are stretched. The light is shifted toward the red end. This is called the Doppler shift, and it applies to light just as it applies to sound. The way an ambulance siren rises in pitch as it approaches and falls as it recedes, the same principle. By measuring the Doppler shift in a star's spectral lines, astronomers can measure how fast the star is moving toward or away from Earth. They can detect the wobble of a star caused by an orbiting planet. They can measure the rotation of galaxies. They can measure the expansion of the universe. All from light. It's a reminder of how much information is carried silently through space. Every beam of light from every star is a message if you know how to read it. The universe is communicating constantly. We've only recently learned a small part of its language. Some supernovae in our galaxy have been visible from Earth with the naked eye and were recorded by observers throughout history. In the year 1054, Chinese astronomers recorded a guest star that appeared suddenly in the sky. It was bright enough to be seen during the day. It remained visible to the naked eye for about 2 years. That event was a supernova. The remnant of that explosion is what we now call the Crab Nebula, a glowing, expanding cloud of gas about 500 light-years from Earth. At the center of the Crab Nebula is a pulsar spinning about 30 times per second, a neutron star, the dense remnant of the star that exploded nearly 1,000 years ago. In 1572, the Danish astronomer Tycho Brahe observed another new star, what he called a nova stella, a new star. He was 26 years old at the time. He observed it carefully for over a year, noting its position and brightness. His observations helped establish that the heavens were not, as Aristotle had claimed, unchanging and perfect. That supernova, now called Tycho's supernova, was in the constellation Cassiopeia. The remnant can still be detected in radio waves and X-rays today. In 1604, another supernova appeared, this one observed by Johannes Kepler. Kepler's supernova was the last supernova in the Milky Way to be visible to the naked eye. Since then, about 400 years have passed without another naked-eye supernova in our galaxy. We are statistically somewhat overdue. In 1987, a supernova occurred in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way about 168,000 light-years away. Called Supernova 1987A, it was the closest supernova to Earth since Kepler's, and the first one close enough to study with modern instruments. Astronomers detected a burst of neutrinos from supernova 1987A, the first direct detection of neutrinos from a stellar collapse. The neutrino signal arrived a few hours before the visible light because the neutrinos escaped from the collapsing core immediately, while the visible explosion took time to work its way out. That detection confirmed in a direct and beautiful way the theoretical picture of core collapse that physicists had been developing for decades. Supernova 1987A is still being observed today. The expanding shell of gas from the explosion has been colliding with a ring of material that the progenitor star shed before it exploded. This collision is producing beautiful structures that telescopes can observe in real time. The ongoing story of a star that died nearly 170,000 years ago, its light only arriving here 37 years ago. There is something deeply moving about that. An event 170,000 years in the making. Light traveling for 168,000 years. Arriving in 1987 and still unfolding today. There is something in the universe that we cannot see directly. Something that doesn't emit light, doesn't absorb light, doesn't interact with light at all. And yet it has gravity, and that gravity shapes everything. It is called dark matter. We know dark matter exists because of its gravitational effects. Galaxies rotate in ways that can't be explained by the visible matter alone. The stars and gas and dust. There must be additional mass distributed throughout and around galaxies to account for the motion we observe. That additional mass is dark matter. What dark matter is exactly remains one of the great open questions in physics. We have many hypotheses. Some involve exotic particles that interact through gravity and the weak nuclear force, but nothing else. Some involve different ideas altogether. None have been confirmed, but we know it's there. And for stars, this matters in a subtle way. The dark matter in our galaxy forms a vast invisible halo, much larger than the visible disk of stars. The Milky Way's dark matter halo extends perhaps 100 times farther than the visible disk. The visible galaxy, all those billions of stars, is embedded in a much larger, invisible structure. Dark matter influenced the formation of galaxies. In the early universe, dark matter began to clump together under its own gravity, forming the large-scale structure of the universe. And the visible matter, the gas that would eventually form stars, fell into those dark matter structures. In a sense, dark matter built the scaffolding. The stars filled it in. Without dark matter, galaxies might not have formed the way they did. The conditions for star formation might have been very different. And life, if it depends on stellar chemistry and rocky planets, might not have had the same opportunity. It's a quiet thought that something invisible and unknown played a fundamental role in creating the conditions for stars, for planets, for us. The universe has secrets we haven't yet uncovered. That's all right. Understanding comes slowly, patiently. We've talked mostly about stars like the sun and about massive stars. But let's spend a little time with the most common kind of star in the universe, the red dwarf. Red dwarfs are small, typically between about 8% and 50% the mass of the sun. They are cool with surface temperatures between about 403 900 degrees Celsius. They glow with a dim reddish light. They are by far the most common type of star. About 70% of all stars in the Milky Way are red dwarfs. The nearest star to the sun, Proxima Centauri, is a red dwarf. It's only about 12% the mass of the sun. It's so dim that even though it's the nearest star to us, it's invisible to the naked eye. Red dwarfs are fully convective. This means that gas circulates throughout the entire star, from core to surface and back, rather than just in the outer layers like the sun. This mixing means that the hydrogen fuel throughout the whole star is available for fusion, not just the hydrogen in the core. As a result, red dwarfs are extraordinarily efficient. They use almost all of their hydrogen fuel, not just a fraction of it. A red dwarf of about 10% the sun's mass might live for 6 to 12 trillion years. That's 6 to 12 million years. The universe is currently about 13.8 billion years old, roughly 0.014 trillion years, which means the smallest red dwarfs have barely begun their lives. They have trillions of years of burning ahead of them. When they finally exhaust their fuel, after trillions of years, they don't expand into red giants. They lack the mass for that. They simply contract slowly into a helium white dwarf cooling quietly over more trillions of years. There's something deeply patient about red dwarfs. Small, dim, slow burning, outlasting all the bright, dramatic stars by margins that are hard to express. Long after all the sun-like stars have faded, long after all the massive blue stars have exploded and cooled, the red dwarfs will still be there. Dim, reddish, quiet, burning on. If any form of life exists near a red dwarf, and some red dwarfs do have planets in their habitable zones, that life would have an almost unimaginable expanse of time available to it. Trillions of years of a steady, if dim, star. We said earlier that space is silent. And that's true. Sound can't travel through the vacuum of space. But that doesn't mean stars themselves are silent. Inside the sun, there are vibrations, acoustic waves, essentially sound waves, ripple through the sun's interior constantly. They're generated by the turbulent motions of gas in the outer layers of the sun. These waves bounce around inside the sun, creating a complex pattern of oscillations. The sun rings in a way like a bell, except very slowly and on a massive scale. The study of these oscillations is called helioseismology, from helios, the sun, and seismology, the study of vibrations. By observing the tiny motions of the sun's surface caused by these internal waves, scientists can probe the interior of the sun in detail. It's a bit like how geologists use seismic waves from earthquakes to map the interior of the Earth. The oscillations reveal the internal structure of the sun. its layers, its rotation rate at different depths, the conditions in its core. Without helioseismology, much of what we know about the sun's interior would be inaccessible. The sun vibrates at many different frequencies. Most of the dominant oscillations have periods of about 5 minutes. The sun's surface rises and falls by about 15 kilometers over and over on a 5-minute rhythm. 15 kilometers in 5 minutes might sound large, but the sun is 1.4 million kilometers across. This is an incredibly tiny oscillation relative to the whole. If you could slow down the sun's oscillations and shift them into audible frequencies, the sun would hum. A deep, complex chord, many overlapping tones. It wouldn't sound like anything in particular, just a hum, a deep resonant hum, a star thinking to itself in a manner of speaking. Stars don't exist in isolation. They live in galaxies. Galaxies are vast collections of stars, gas, dust, and dark matter, all gravitationally bound together. The Milky Way contains somewhere between 200 and 400 billion stars, and the observable universe contains something like 2 trillion galaxies. 2 trillion galaxies, each with hundreds of billions of stars. The total number of stars in the observable universe is estimated to be around a septillion, a 1 followed by 24 zeros. Each of those stars is a sun. Each one has its own life story. Each one will eventually die. Most will end as white dwarfs. A fraction will end as neutron stars. A small fraction will become black holes. And all of them, through their deaths, will enrich the gas around them, making the conditions for future stars and planets a little richer. Galaxies themselves evolve over time. In the early universe, galaxies were more active. More star formation, more supernovae, more turbulence. As the universe has aged, galaxies have generally settled down. Star formation has slowed in most large galaxies, but it hasn't stopped. New stars are still forming in the Milky Way at a rate of perhaps a few per year. Not the intense bursts of the early universe, but a steady trickle. Some galaxies are colliding right now. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, about 2.5 million light-years away, is moving toward us. In about 4 billion years, it will begin to merge with the Milky Way. The merger won't be violent in the way you might imagine. Galaxies are mostly empty space, and the individual stars almost never collide. But the gas clouds will collide and compress, triggering bursts of star formation. The shapes of both galaxies will be distorted and scrambled. The end result, after a billion years of merging, will be a large elliptical galaxy. Our descendants, if any exist, would see a very different night sky. But that's a very long time away. And whatever happens, the stars will keep doing what stars do. Being born, burning, dying. The particular shape of the galaxy around them doesn't change that fundamental story. Let's take a moment and think about light. Light is what we see when we look at stars. It's what carries the information from distant stars to our eyes. It's the medium through which we know the universe. Light travels at about 300,000 kilometers per second. That is the fastest that anything can move as far as we know. And at that speed, it takes time to cross the enormous distances of space. Light from the moon takes about 1.3 seconds to reach Earth. Light from the sun takes about 8 minutes. Light from the nearest star takes about 4.2 years. When we look at a star 1,000 light-years away, we see it as it was 1,000 years ago. When we look at a galaxy 10 million light-years away, we see it as it was 10 million years ago. The universe we see is not the universe as it is right now. It is a mosaic of different moments in time, each at a different depth in the past. There is no such thing as now when it comes to looking at distant objects. There is only then How far then, depending on how far away the object is. All the light from all the stars you've ever seen in the night sky is ancient. Some of it is a few years old. Some is hundreds of years old. Some is thousands of years old. It traveled across the void in complete silence and emptiness, and then it struck the back of your eye and became a sensation of warmth or brightness. Ancient fire arriving silently after a long journey. There's something very calming about that image. Light as a traveler, ancient patient, crossing immense distances over long times to arrive here in this quiet moment, just as you are arriving at sleep after a long day. Both journeys ending in the dark, in the very far future, after all the sun-like stars have died and even the red dwarfs have begun to wind down, the universe will be a different place. The last stars to shine will be the smallest red dwarfs, dim and reddish, burning so slowly that their light would be barely perceptible from a distance. Around these last stars, if planets remain, the light would be faint and reddish. Not the warm yellow of sunlight, but a dusky, dim red. Permanent twilight, almost. Any life that persisted near these final stars would live in a very old, very quiet universe. Most of the bright stars would have faded billions or trillions of years ago. The night sky, as seen from such a world, would be mostly dark. Most of the galaxies dim and depleted of new stars would have faded. The universe would be much, much darker than it is today. And still the last little red stars would be burning. Patient, dim, slow, holding on, until they too finally exhaust their fuel, and cool, and darken. And after that, the universe enters a very long, very dark era. White dwarfs and neutron stars and black holes drifting slowly through a cold, dark, expanding cosmos. Very little light, very little warmth. It is a very long way off, trillions upon trillions of years. And what happens after the last stars die is a story for another night and another sleep. For now, the stars are still burning. The universe is still young. There is still light, and you are here in the warmth of it. We are winding down now. The body settles more deeply into the night. The mind, which has been gently turning over ideas about stars and death and time, is beginning to grow quieter. That's the right direction. Let's review what we've covered very gently one last time. Stars are born from clouds of gas. Gravity causes the cloud to collapse. The center heats up until nuclear fusion begins. A star is born. The star spends most of its life burning hydrogen into helium. This is the main sequence, a long, stable, balanced phase. When the hydrogen in the core is exhausted, the star evolves. It expands. It becomes a giant. For stars like the Sun, the giant phase ends in a planetary nebula, a beautiful shell of glowing gas surrounding a small, dense white dwarf. For more massive stars, the end is more dramatic. Layers of heavier elements are built up in the core until iron, and then the core collapses in less than a second, and a supernova blows the star apart. What's left is a neutron star or a black hole. Through all of this, the matter that was in the star is returned to the galaxy, enriched with heavy elements, available to form new stars, new planets, possibly new life. The cycle continues, and you, reading this or listening or half asleep, are part of that cycle, made of ancient stellar material, alive on a rocky planet that formed from a cloud of enriched gas, breathing oxygen that was made in stellar cores and scattered by stellar winds. You are a temporary and local gathering of ancient materials, alive and aware in this brief slice of cosmic time. And that is a wonderful thing. And now, at last, we come to the very end. It's late. The world outside is quiet. The stars, if you could see them, are doing what they've always done. Burning, balanced, patient, each one on its own long road. The sun is on the other side of the earth, right now shining steadily on whatever part of the world faces it, fusing hydrogen, maintaining that ancient balance, warm and reliable, as it has been for 4.5 billion years. Everything we've talked about tonight is real. The nuclear reactions are real. The red giants are real. The supernovae are real. The white dwarfs and neutron stars and black holes are real. The universe is genuinely this large, and genuinely this old, and genuinely this patient. And you are part of it, not a small part despite appearances, because you are the part that can look out and wonder, the part that can ask questions and find answers, the part that can tell the story of stars dying and feel something about it. As far as we know, that kind of awareness, that wondering, is rare in the universe. We've only found it in one place, here. So while the universe is enormous and old, what you are is also remarkable. A small and temporary complexity in a vast and quiet cosmos capable of understanding the cosmos itself at least a little. Let the breath slow. Let the thoughts drift. The stars are out there quiet and ancient and burning. And you are here quiet and warm and alive. And for now, that's everything. If you liked the video, please support us. Subscribe to our channel, leave a comment, and gently tap the like button to motivate us to create more of these quiet, peaceful journeys. Your support helps us continue sharing the stars, the universe, and these stories. Thank you for being here, for listening, for exploring the cosmos with us. Good night.